Good morning all. Welcome back to the lecture series on Engineering Thermodynamics subject. My name is Devinder Singh Thapa, Assistant Professor in Mechanical Engineering Department of Silver Oak University. This is your lecture number 2. In our previous lecture, we discussed about the chapter number 1, that is Introduction. Then we have gone through number of terminologies, definition and various concepts. And let me assure you, those terms or concepts we will be using in our upcoming chapters. So try to revise those concepts on regular intervals. Okay. Now in our today's lecture, we will try to cover the number of laws of thermodynamics, that are 0th law, first law. Then we will try to cover the second law and third law. And let me assure you, these laws are applicable to every mechanical machines or devices that we are using on daily basis. Okay. Now we will start with the 0th law. 0th law is also known as temperature law. Why it is called temperature law? Because it gives you the values of temperature. For any instrument, for any appliances, if you want to calculate the temperature, and that temperature calculation will be done on the basis of 0th law. So first we will go through the definition, then I will elaborate the concept, and then maybe I will give you 1 or 2 practical examples where we are using the 0th law. Same manner, this is the most fundamental law and very simple law. So just I will read the definition. It states that when the two systems are in thermal equilibrium with the third system separately, then they themselves are in thermal equilibrium with each other. It means if we have a 3 system number A, B and C, then it is trying to say that if A is in thermal equilibrium with B, and again A is in thermal equilibrium with C separately, so automatically other two system will also be in thermal equilibrium, that is B will be equal to C. We will be in thermal equilibrium with the C. This point is clear. This is somewhat like your mathematics things where we were writing x equal to y, x is equal to y, then we used to write x equal to z. So if your left hand sides are equal, if your left hand sides are equal, then automatically your right hand side will also be equal. It means y is equal to z, that we have studied in mathematics algebra section. So in the same manner, 0th law is also stating same manner. A is in thermal equilibrium with B, and separately A is also in thermal equilibrium with C, then automatically these two will also be in thermal equilibrium. And where we will be using this application of this 0th law will be in the temperature measurement. Like we will place 3 bodies, and then we will leave those bodies to come in thermal equilibrium. Then automatically we will be getting the unknown body temperature from that very experimental setup. Okay. Now the application of 0th law. Application includes like this is your typical example where a hot cup of tea is being left in the surrounding. Now what is going to happen in this case is that this hot cup of tea whose temperature is higher, it is going to lose its heat to the surrounding. In the reverse process, your surrounding which is at the lower temperature is going to gain heat from this hot coffee. So ultimately what is going to happen, we have already studied about the term heat. Heat is directly proportional to delta T, that is change in temperature. So when we increase this delta T, your heat is going to increase. If we are going to decrease the temperature, then automatically your heat is going to be released or reduced. So your T is releasing the heat, means T is the temperature of this cup of tea is going to decrease from, suppose, from 30 to 20. Same manner, the surrounding temperature which is let it be around 15, then this surrounding is going to gain heat and it is going to attain, suppose, somewhere temperature approximately around 20 degree. So this heat transfer will continue to occur until and unless both the temperature of your cup and the temperature of your surrounding is going to be equal, and at that very point we will say that they are in thermal equilibrium. So at that point we will measure the temperature T by using any thermometer device. Clear? So this is your basic day-to-day life practical example of zeroth law that we are going to observe. Now, so we will go through some more application. Another one is your mercury thermometer, which was also working in this zeroth law application. So in mercury thermometer, the height of the mercury level is been increased, and this increment is because of increase in temperature. So it is suggesting that the temperature rise will be depending on the height it is being raised inside the mercury section. So same manner, a cold glass of water eventually cool downs. Then another example, in your daily life you are observing fruit and vegetable kept inside the refrigerator achieve the fridge temperature. It means what? If you take bring those fruits and vegetables from outside, then obviously their temperature will be higher, and once you kept that those vegetable and fruit inside the refrigerator, then what is going to happen? Those fruit and vegetable will start losing their heat, and it automatically means their temperature will reduce, and that heat will be gained by the freeze, and that temperature is going to increase of that refrigerator. Automatically at one point the thermal equilibrium will be attained, and at that point the temperature of vegetable and fruit will be same as your refrigerator temperature. Is it clear? So these were the daily life examples of your zeroth law. It is again highly conceptual or theoretical law that we will be using. Now coming back to the first law of thermodynamics, it is very important law, and now your main study or core technical study of thermodynamics will start from this very topic, that is first law of thermodynamics. Now first I will elaborate the experiment that was given by Joule, also known as Joule experiment. Now before going to this setup, I will like to tell you that all the results of your first law of thermodynamics, all the results will be obtained only on this Joule experiment, only because of this Joule experiment. One of the great scientists, Joule, you might have heard about him. There are a number of parameters or SI units that we are using for any energy, kinetic energy, potential energy, any type of work we are doing. Everywhere we are putting a SI unit, that is Joule. So only on the name of this great scientist is a number of experiment in the field of thermodynamics. That is why we are giving this SI unit of Joule. So now coming to the experimental setup, firstly I will tell you the apparatus what he is having, what he installed in the system. He has taken a beaker or a container. Inside that container he put some amount of fluid or water, let it be any fluid. Then he connected that fluid system with a paddle wheel system. This is your paddle wheel system that I am highlighting, and that paddle wheel system is being connected with a pulley system, and that is being connected with some amount of weight. Now what he did in number of experiment, he put some amount of weight continuously. He put some amount of weight means mg, mass into gravity. So he continuously increased the weight from 10 kg to 20 kg to 15 kg. So number of times he increases the weight. Now what is happening inside? On increasing the weight, continuously this paddle wheel system will start rotating. So when this wheel will rotate, it will lead to the generation of some sort of vibration energy, and that vibration energy will create some sort of agitation inside the fluid, and that fluid continuously start to rotate along with this wheel. So what is going to happen? By this rotation, the fluid heat will going to be increased. The fluid kind of energy or heat is going to increase because of this agitation or rotation. So slowly your fluid will start gaining some amount of heat, and gaining amount of heat, we have already studied that it will lead to the increment in the temperature from T1 to T2. So continuously your water temperature is going to be increased. Why it is going to be increased? Because all this setup is being completely insulated from the outside, means there will be no heat loss to the surrounding. All the heat that will be generated inside the system will remain inside the system. So continuously your weight is being put in this side. You continuously it will lead to the rotation of your fluid, and that very rotation will increase in the temperature of your fluid. by gaining some amount of heat, its temperature is going to increase, and that very temperature we will measure by using any thermometer. So continuously what he obtained, that continuously your work is being transferred into some amount of heat. So again we have already told you that regarding the thermodynamic subject, it is a study of heat and work and their interconversion from one form of energy into the another form of energy, or the transformation of heat into work. So same setup, he did number of experiment 1000 times, 2000 times, then finally he obtained some amount of results. So those results we are going to study in first law. So first law result after Joule experiment that we will go through now. So he concluded two types of result. First, this very setup give you a result that is known as summation of cyclical integral of del Q will be equal to the cyclical integral of dW. Yesterday we studied about the processes and cycles. So if a complete cycle is occurring inside the system, for a system undergoing a cyclic process, that is a complete cycle that is being happening in that experiment, that net work of net heat transfer will be equal to net work transfer. Same thing that I explain you, del Q integral will be equal to delta W, means change in any amount of work will be equal to net change of any amount of heat. They will be exactly equal to each other only and only when it is a cyclic process. One means one complete cycle is occurring. Clear? So it states that heat and work are mutually convertible. They can be converted from one form, heat into work, or we can convert work into heat. Now this is for cycle. Now for a process, for a single process, what is going to happen? What was the result of Joule that we will study now. So this is all about the cycle, and this concludes your Joule experiment. Now what is going to happen? First law for a process. Suppose we are going from point number 2 to state number 1, from state 2 to state number 1. So this is a single process. So this, for a single process, what is your first law of thermodynamics? So it will be equal to change in heat, amount of change in heat will be equal to change in work plus delta U. This is very important term, delta U, that is change in internal energy of that very process. Why? Because it is only a process. We are going from 2 point to 1 point, and we are not going to come back from 1 to 2. Had we come back again, then it will be a cycle, then that previous result was valid. Now this is known as first law of thermodynamics for a process. So now we will do number of applications, then we will try to solve some numericals on these very formulas, then it will be more clear to you. Same statement, delta U we have taken in the left hand side, it will be Q plus W. Clear? And their sign we have already discussed in your last lecture. Q and W will can be positive or negative depending on the conditions. A perpetual machine motion of first law does not exist. It means it is also known as PMM1, or for when we study second law, then it will be PMM2. So these machines does not exist, means there is no machine that is being still made that will violate the first law of thermodynamics. It automatically means first law of thermodynamics is valid everywhere, and it is sometimes also known as energy conservation law. Okay, that energy can neither be created nor be destroyed. It will be transferred from one form of energy into the another form of energy. This statement might have heard a number of times in your physics subject in 8th or 10th class. So this is all about the theory of your first law of thermodynamics. Now quickly we will go for few significances of first law of thermodynamics. It gives you the relation between heat and work that is being established by the first law of thermodynamics that we know by the Joule experiment. Both heat and work are equivalent to each other. That is valid only for a cyclic process we have studied. The exact amount of heat surrounding will be, one will be losing heat and another will be gaining the heat. System will lose, then surrounding will gain. Applied heat is equal to the sum of work done and change in internal energy, that is delta Q will be equal to W plus delta U, that expression we have seen for process. Then energy is constant for isolated system. Those systems we have studied yesterday. I told you the isolated system, there will be no heat interaction, there will be no work transfer. So automatically delta U or delta E will be equal to 0, that is E1 will be equal to E2. Simple. Now there are a number of application of first law of thermodynamics. We already know it is energy conservation law, so it will be applicable everywhere. That terms or application related to mechanical common applications are your heat engine. So it is the most common practical application of first law. Thermal energy will be converted into and mechanical, and that by a heat engine. So heat engine, what is going to happen? Your all the thermal energy that is being created or generated by the burning of fuel will be converted into mechanical energy, and that mechanical energy will lead to the motion of your machines or IC engines, whatever you are using in heat engine. Then another applications are like refrigerator, air conditioning and heat pump that you are using daily basis. These are the mechanical, where the mechanical energy we have to supply in the form of electricity, and that will be converted into heat, or it will be converted into heat in the form of condenser that we will be discussing in the second law in the upcoming lectures. Okay, although melting processes all these are the application of your first law. This is the expression for melting expression, where delta U will be equal to ml. And for isothermal process, what is going to happen? Isothermal means your temperature is going to remain same, means T1 will be equal to T2, then automatically delta T will be equal to 0. Now your delta U, that is internal energy, is directly proportional to delta T, that is your MCV delta T. So if this is your 0, then it will become 0. So for isothermal process, net amount of heat added will be equal to net amount of work developed. This is the simple expression for isothermal process. Also you can analyze for some other processes like adiabatic process, isochoric, isobaric process that you have already studied in your BME subject in first year. So that were applicable. Now this is a typical example. Number of example you can now solve for different types of processes by using the first law of thermodynamics. Here the parameters that are being given, a system. Firstly I will read the question. A system undergo a cyclic process composed of 4 processes. The heat transfer to each process are 400, 365, minus 200 and 250. The respected work done are 140, 0, minus 50 and 0. The is data constitution for the first thermal. You have to justify or validate the first law or Joule experiment. So what was your Joule experiment? Delta Q will be equal to delta W. So whatever amount of delta Q summation of heat we have done, it is coming out to be 85. Then for the same cyclic process, the summation of integration of delta W is also coming out to be 85. So it automatically means it justifies your first law of thermodynamics. Clear? So in this manner, number of numerical, like one more numerical will be there, where they will give you the 3 values of delta W or 4 values of Q, then they will ask one unknown value. In this manner we will solve some amount of numericals. Now the most important application of your first law of thermodynamics, from where your numerical aspects will also start. All your competitive exams, suppose you will be going for GATE exam, that is graduate aptitude test in engineering exam, or any PSU exams in your upcoming, after reaching to the final year, you will be eligible for all those exams. So number of examples or questions will be asked from this very topic. So what is a steady flow, or most commonly known as steady flow energy equation for first law? So first law steady flow energy equation is very important. Its applications are number of applications like nozzle, diffuser, the working of turbine, compressor, those things will be asked. Now basic definition for steady flow we have already gone through. We already know that there are 4 types of flow: steady flow, unsteady flow, or the uniform flow, non-uniform flow, that we have heard about number of times. Any parameter that is not changing with respect to time, means you are supplying some amount of velocity. Suppose you at 9 a.m. you have supplied the velocity with 10 meter per second, then at 10 a.m. also you are supplying with the same velocity. So means any parameter that is not changing with respect to time will be giving you a steady flow. Clear? So that very thing we have to study in this whole section of steady flow energy equation. There will be a number of assumptions that we are assuming, that mass flow through the system remains constant, flow is uniform in composition, means there is no change in composition of fluid, the only interaction between the system surrounding are work and heat, no other parameter like enthalpy or other things. State of fluid at any point remain constant with respect to time, that is itself a steady flow. In analysis of only potential, kinetic and flow energies are considered, and those only forms of energies we will be considering. So these are your number of assumptions. Now we will go for the small derivation for a steady flow energy equation in a closed system. Then we will go for its application. So first law definition we have already gone through. Energy can neither be created, means total energy will remain constant for a system. That is the expression for this steady flow energy equation. Now we are going to the derivation. So I will try to give you the elaboration of this very experimental, and the numerical derivations you can practice in your notebook. So what if this is your closed system, then what we know, total amount of energy coming into the system will be, and minus total amount of energy or work going out from the system, it will be equal to the net rate of change in the internal energy of the system. Means suppose 100 kilojoule of heat is coming, you are getting some 60 kilojoule of work, then automatically those 100 minus 40, 60 kilojoule of energy will be stored inside the system in the form of change in internal energy. That very definition we have studied. So now this change in total energy of the system will be the summation of internal energy, kinetic energy, potential energy, whatever form of energy we are considering. Only two forms of energy we are considering, kinetic energy and potential energy, plus internal energy. So this delta E total will be the summation of U plus kinetic energy plus potential energy. So this is the final expression for closed system. Q minus W will be equal to delta U plus delta K plus delta P. Now considering 2 points of any section, let the point number 1 and 2, and this change in kinetic energy will be written half mb square minus half mb2 square. Same manner, change in this delta Z will be equal to G into potential energy change will be Z2 minus Z1, and by conversion factor we are dividing by 1000. Nothing else we are doing, only those delta U will be written as from suppose I am considering we are traveling from point number 1 to point number 2, means our flow is being from point number 1 to point number 2. So what is the change in delta U? It will be U2 minus U1. Same manner, what is the change in kinetic energy? V2 square minus V1 square upon 2. Same potential energy G Z2 minus Z1. So this lengthy expression is coming, but it is very basic or fundamental expression that we will be using number of time to solve a number of problems in your steady flow energy equation. Clear? So now we are trying to generalize the expression, and where are the application of this steady flow energy equation. There are large number of applications. Practical devices we are using. Nozzle we are using to increase the velocity of any fluid. Then we have a diffuser to decrease the velocity by increasing the pressure. We are having turbines that are being used to generate the electricity. Compressors to increase the pressure. Throttling valves like your capillary tubes we are using in your refrigerator, heat exchanger, or any number of mixing devices. So all these are the example of steady flow energy equation, and let me assure you these are very important devices that we daily observe. So now we will try to apply this very steady flow energy equation to each and every device individually. First we will apply to nozzle and diffusers. Now these are the things you have to practice mathematically also in your notebook, so that it will be more clear. Okay, nozzle we know that device used to increase the velocity of the fluid at the expense of pressure, means by the pressure energy will be converted into kinetic energy. So automatically your velocity or kinetic energy is going to increase. Velocity is going to increase means half mb square kinetic energy is going to increase by decreasing the pressure energy, because total energy will remain constant. One form of energy will be converted into another form. So here the pressure energy is being converted into kinetic energy. Exactly reverse is the case of diffuser, where the pressure and where the kinetic energy will be converted into pressure energy. So it will lead to the decrement in the velocity. Here the velocity will increase, and all the other parameter we will assume like it is being insulated. This dotted line is showing that the nozzle is being insulated, means there will be no heat loss to the surrounding. So Q will be equal to 0. There is no connection of any shaft, nowhere any shaft is being connected, so your work done will be 0. Same the height, that is the potential energy. We are considering these as the horizontal nozzle. Mostly we will consider horizontal ones. So there will be no change in height, means no change in the potential energy. So this is all about the nozzle, and the very equation that we have derived we will apply here by putting those assumptions like q barabar 0, w barabar 0, height is same. We are going to get this expression, final expression. Only these two parameters, enthalpy change and u2 minus u1, or kinetic energy change, will be there. Only velocity and your enthalpy change will be there. So same expression again we have written here, so nothing to worry. Only the final result, that is we are getting h1 plus v1 square by 2 plus he plus ve square by e for exit. Okay, where we can also have a multiply it by mass flow rate, rho ab, density, area into velocity. So this h1 v1 square 2 plus is will be equal to h2 plus v2 v square by 2 will be the final result that we have to remember, or otherwise nothing to remember. Only apply the assumption to the steady flow and energy equation, you are going to automatically going to get this same result. So same result is also valid for diffuser. So this C1 CT, in this manner we are going to get the velocity at the exit, C2 or V2, whatever you want to write. C2 will be in this manner. By arranging these things we are going to get the values of velocity at the exit for nozzle or also for diffuser. Now moving forward, another practical device where the steady flow energy equation will be applicable will be your turbine. Now we study about the turbines. Firstly, we need to remember turbine generators are the power producing devices. They are going to give you the power or electricity. Okay, whereas compressor, pump, refrigerator, these are power consuming devices. Now how this is going to generate you the power or work? It is being connected by a shaft, so definitely there will be a shaft work. If shaft is rotating, you are going to get the shaft work. Then this whole turbine is being insulated. We are assuming it is being insulated, means q will be equal to 0. Same manner we are assuming this turbine to be horizontal, delta z will be 0. Then we are also assuming that your velocity changes are negligible, so there will be c1 will be approximately equal to 0. So all these things are being assumed, and then these are being applied to steady flow energy equation. Then what we are going to get? We are going to get q barabar 0, C1 C2 are almost equal, we are considering. So directly we are going to get the value of W. It will be equal to H1 minus H2, that is higher enthalpy change, H1 minus lower enthalpy change. So it will give you a positive work. Positive work, automatically we have discussed the positive sign of work means work done by the system, work done by the turbine, that we have studied in first lecture. So it will give you the positive work. Clear? Exactly opposite of this will be your compressor. Compressor will be your power consuming device. Power consuming device means negative work. So this is your compressor, which is used to increase the pressure of any appliance where we want to increase the pressure. So it will consume the power in the form of electricity. We will supply the work to the system. So then we will apply this steady flow energy equation. Again our assumptions are somewhat similar. Delta Z 0, velocity change 0, and then automatically those C1 C2 will be approximately equal to each other. Velocity is at inlet and outlet of the flow of air through the compressor. Then we have assumed that this is being insulated, q will be 0. So directly we are going to get W2 will be equal to how much? H2 minus H1, and that W work is done on the system. So this W will be going to be definitely negative work. So that is why we call this compressor as the power consuming devices. So this is another application of steady flow energy equation. Don't go for the remembering of these formulas. Just try to remember one single formula of steady flow energy equation that we derived in the previous slides. Then apply these conditions, assumptions. Just remember, try to highlight these assumptions and then put these assumptions in the steady flow energy equation. You are definitely going to get the final result, and that will be absolutely correct. Now heat exchanger are the devices that are being used to exchange heat from one fluid to the another fluid. So in this manner there are a number of examples of heat exchanger. One is your boiler that we have already used in your BME subject. We have gone through steam boiler chapter. we know about the boilers, it is being used to exchange heat with each other. So now horizontal, again assumption delta Z 0, C 0, work, there is no work done, so heat transfer will be equal to change in enthalpy here. Heat transfer H will be equal to, Q will be equal to S2 minus H1, S2 outlet minus in1 H1 enthalpy at the inlet. That will be the heat that you will be you have to supply to the steam in order to drive the steam, and then you are going to get the electricity. Then opposite of this boiler that is used to increase the heat, we have a condenser that is used to release the heat. So its expression will be exactly, all the assumptions will be same. You will going to get the reverse expression to the boiler, that is H1 minus S2 you are going to get here in condenser. Again, it is a type of heat exchanger. All your refrigerator, condenser, boilers, these are your heat exchanger that are used to exchange heat. Suppose here we are supplying steam, then in this direction we are supplying water. This steam will exchange heat, or it will supply its heats to the water. Clear? So in this manner we will apply another device, last device, that we application of this steady flow energy equation. We will have a throttling valve. So these are flow restricting devices that are used to restrict the flow, that you can easily adjust here a type of valve, a type of porous plug, or a capillary tube that we are using in the refrigerator. These are the examples of throttling devices. Now what is the special feature of these throttling devices? These are isenthalpic processes where we will apply the steady flow energy equation, then we are going to get this expression. All the parameters like work done, heat transfer, change in height, change in velocity are 0 or negligible. So only thing we are remaining with is H2 minus H1. It automatically means it is equal to 0, H2 will be equal to H1, means their enthalpies are same. That is why we call this throttling process as the isenthalpic process. Clear? So this concludes your applications of steady flow energy equation. Today we have gone through. Now in your next lecture we will be going for second law, and before going to second law I will explain this limitation of first law, because by understanding the limitation of first law, then only you will be able to understand the working of second law. So we will start with the limitation of first law in your next lecture, then we will go for the second law study in detail. Then finally in our fourth lecture we will go through these number of cycles we will studying, like Brayton cycle, Rankine cycle, and their animation videos we will play, and then we will try to understand those cycles in detail. Okay, so we concluded the first law. Now we will start in the next lecture with the support the second law from the point of limitation of first law. Then we will study in detail second law, their application, then entropy, exergy. Those things we will be studying in our upcoming lecture. Okay, thank you for attending the lecture. If you have any doubt or query, you can ask me in next lecture. Thank you for attending the lecture. We will meet in the next lecture.